Hi, my name is Lyndon Solganic.
And I'm Grace Godinez, and this is our Optics 380 Lab 9 on diffraction with Harsha Pradeep.
In part A, we observed the diffraction pattern created by various apertures. So we observed an LED, a laser diode on our camera, and we looked at a single slit aperture, 0.2, 0.3, and 0.45 millimeter spacing double slit apertures, triangle, square, and circle. And we looked at the image of the aperture on the camera and moved the camera and the lens closest to it along the optical rail to look at the Fresnel zone and then find the Fraunhofer diffraction pattern, which is the Fourier pattern of the aperture. Finally, we use MATLAB to compare the circle's area pattern to the theoretical area pattern intensity profile. Here's our results for the single slit, and on that second row there we can see the Fresnel zone as it transitions from the aperture to the Fraunhofer. Here's the double slit. Next, size up double slit, and then our largest double slit. And we can see as the slit spacing increases, the distance between bright fringes decreases. Here's the triangle, square, circle with the area pattern on the right.
We determined key characteristics of a laser beam using the data ray software to collect data on 15 different detector positions along the optical rail. We collected the given widths along the X and Y axis, which are highlighted in red down here. We then plotted all of our data points using Excel and used Excel's automatic best fit line, polynomial best fit line tools to get the plot below along both X and Y directions for distance versus beam profile. Then we took those two best fit lines and applied our quadratic expansion as detailed in the procedure to them, to each of our A, B, and C values in the previous best fit lines, and used those to derive calculations for beam waist diameter, divergence, and numerical aperture. Ultimately, we got waist diameters of 11.3 micrometers, 15.38 micrometers, and 0.018 degree and 0.013 degree beam divergence half angles, and finally numerical apertures of 0.867 and 0.697. In part A, we were able to successfully examine the Fraunhofer diffraction patterns of several different slits, and we measured intensity profile of area disk created by circular aperture and compared to expected intensity profile. This part helped us gain a better understanding of diffraction patterns and how distance along optical axis change the pattern that we see. In part A, we were able to see the desired characteristics of our commercial beam and get the desired Gaussian beam output.